Linux has always been known as the operating system that quietly powers the internet, servers, supercomputers, and millions of devices around the world. Yet for many everyday users it remains something mysterious, something powerful but slightly intimidating. For decades, Windows and macOS dominated the desktop space, while Linux built its reputation behind the scenes, evolving slowly but steadily through community collaboration and open innovation. But every once in a while, something happens in the Linux world that feels less like a small update and more like a turning point, a moment when the entire trajectory of the operating system shifts. And recently, something exactly like that happened. A new feature, a new direction, and a new wave of development has many experts saying the same thing. Linux may have just changed forever. To understand why this moment is so important, we need to take a quick look at how Linux traditionally evolved. Unlike commercial operating systems that are controlled by a single corporation, Linux grows through contributions from thousands of developers around the world. Companies like Red Hat, Canonical, Google, Intel, AMD, and countless independent programmers all contribute to the Linux kernel and the ecosystem around it. This decentralized development model has always been Linux's greatest strength, but it also means big changes often take years of debate, testing, and refinement before they finally arrive. So when the Linux community collectively pushes forward with a transformative feature, it's not just a random experiment. It's something that has been carefully considered, tested, and embraced by the community. The feature that has everyone talking right now revolves around something many people never think about: how the operating system interacts with applications, hardware, and security at the deepest level. Traditionally, Linux distributions have relied on package managers and system libraries that vary between distros. Ubuntu uses apt and dead packages. Fedora uses DNF and RPM. Arch Linux uses Pacman. And each of these systems has its own repositories, dependencies, and update structures. While this diversity gives Linux flexibility, it also created one of the biggest obstacles for developers and new users. Applications often needed to be packaged separately for different distributions, dependencies could break, and compatibility could become complicated. Over the past few years, developers began working on a new approach that would fundamentally change how Linux applications are delivered and executed. Instead of relying entirely on distribution-specific packaging systems, applications could be bundled in universal formats that run across almost any Linux system. Technologies like Flatpak, Snap, and API Image started to gain traction. But recently, these technologies have evolved dramatically. The newest improvements integrate deeper system, sandboxing, better hardware access management, faster launch performance, and seamless updates that feel more like modern mobile operating systems. What makes this development so revolutionary is how it changes the user experience. Imagine installing an application on Linux the same way you would on a smartphone. You open a software store, click Install, and the application runs perfectly, regardless of which distribution you're using. The system automatically manages permissions, updates happen quietly in the background, and compatibility issues almost disappear. For many people who avoided Linux because they feared dependency conflicts or command line troubleshooting, this new approach removes a huge barrier. But the real story goes deeper than convenience. Security is where this new system begins to truly outshine traditional desktop operating systems. Each application runs inside a controlled sandbox environment, isolated from the rest of the system unless specific permissions are granted. That means an app cannot simply access your files, camera, or network without your approval. If the application becomes compromised, the damage it can do is extremely limited because it cannot escape its sandbox easily. This architecture is something that security experts have been pushing toward for years, and Linux is now implementing it at a level that rivals or even surpasses modern mobile platforms. This security model also addresses one of the most common attack methods in desktop computing: malicious software exploiting system-level access. On traditional operating systems, many applications have broad permissions by default, which creates opportunities for malware to manipulate files or inject code into other processes. With the new Linux approach, those permissions are strictly controlled. Applications request access to specific resources, and the operating system mediates those requests. It's a design philosophy that emphasizes least privilege computing, meaning software only gets the exact access it needs and nothing more. Another major advantage comes from system stability. Historically, installing or updating software on Linux could occasionally create dependency conflicts, especially when mixing third-party repositories or experimental packages. These issues weren't extremely common, but when they happened, they could be frustrating. Universal application formats eliminate many of those problems because each application carries its own dependencies. That means an update to one application is far less likely to break another. The system becomes more modular and resilient. Performance has also improved dramatically. Early versions of universal packages sometimes suffered from slower, STARTUP times, or increased storage usage because each application included its own libraries. Developers have since optimized shared runtime environments, deduplicated common libraries, and improved caching mechanisms. As a result, applications now launch faster and use system resources more efficiently. In many cases, the performance difference compared to traditional packages is negligible or even better. This shift is also changing the relationship between Linux distributions and software developers. Instead of packaging their applications separately for dozens of distributions, developers can build a single universal package that works almost everywhere. That dramatically reduces development overhead and makes Linux a far more attractive platform for commercial software. Over the past few years, we've already seen major applications like Discord, Spotify, Steam, and Visual Studio Code adopt these packaging methods. With the latest improvements, even more developers are expected to follow. And this leads to something truly interesting. For decades, one of the most common criticisms of Linux on the desktop was the lack of mainstream applications. While Linux had excellent open-source alternatives, some users still needed specific commercial tools that were only available on Windows or macOS. The new packaging ecosystem removes one of the biggest technical barriers that prevented companies from releasing Linux versions of their software. When developers can target a single universal format instead of dozens of distributions, supporting Linux suddenly becomes far more practical. The gaming world is another area where Linux has undergone a dramatic transformation. Valve's investment in Proton and the Steam Deck has already made thousands of Windows games playable on Linux with minimal effort. Combined with universal packaging and containerized environments, games can now run in optimized environments that ensure consistent performance across distributions. The result is that Linux gaming is no longer a niche experiment but a rapidly growing ecosystem. Hardware compatibility has also improved significantly. Modern Linux kernels include extensive support for new processors, graphics cards, and peripherals. Companies like AMD and Intel contribute directly to kernel development, ensuring their hardware works seamlessly. NVIDIA has also made improvements with better open-source driver support. As hardware vendors continue collaborating with the Linux community, the traditional gap between Linux and other operating systems in terms of hardware support continues to shrink. Another key aspect of this transformation is how Linux is embracing containerization and virtualization technologies that originated in the server world. Containers allow applications to run in isolated environments with their own libraries and dependencies, ensuring consistency regardless of the underlying system. These technologies are now influencing the desktop experience as well, enabling powerful development environments, secure testing environments, and highly customizable work. Developers, in particular, are benefiting enormously from this new direction. Instead of worrying about system configuration differences across machines, developers can package their entire development environment into containers or universal packages. That means code behaves the same way, whether it runs on a laptop, a workstation, or a cloud server. This consistency dramatically reduces the "it works on my machine" problem that has plagued software development for decades. Meanwhile, the Linux desktop itself has been evolving visually and functionally. Desktop environments like GNOME and KDE Plasma have introduced smoother animations, improved Wayland support, better touch interfaces, and highly customizable layouts. These environments now feel modern, polished, and competitive with any commercial operating system. Combined with the new application ecosystem, Linux desktops are becoming more user-friendly than ever before. Wayland deserves special attention in this conversation. As a successor to the aging X11 display server, Wayland introduces a more secure and efficient graphics architecture. Applications communicate with the compositor in a more controlled way, reducing the risk of input snooping and improving rendering performance. The transition to Wayland has taken years, but many major distributions now use it by default, marking another significant milestone in Linux's evolution. Energy efficiency is another area where Linux has quietly gained an advantage. Modern kernels include sophisticated power management features that optimize CPU usage, reduce background resource consumption, and extend battery life on laptops. When combined with lightweight desktop environments, Linux systems often run faster and more efficiently on older hardware compared to Windows or macOS. For privacy-conscious users, Linux also offers a level of transparency that proprietary operating systems simply cannot match. Because the source code is open, developers and security researchers can inspect how the system works, identify vulnerabilities, and ensure there are no hidden data collection mechanisms. While many distributions include optional telemetry for improving the system, users typically have full control over what data is shared. The impact of these changes is beginning to reshape the broader technology landscape. Governments, educational institutions, and enterprises around the world are increasingly adopting Linux for cost savings, security, and independence from proprietary platforms. As Linux desktops become easier to use and more compatible with mainstream software, the potential user base expands even further. Of course, this doesn't mean Windows or macOS will disappear overnight. Both platforms still have enormous ecosystems and loyal user bases. But the gap that once separated Linux from its competitors is narrowing rapidly. Features that were once considered weaknesses are being replaced with modern solutions that combine flexibility with simplicity. Perhaps the most fascinating aspect of this transformation is how it reflects the core philosophy of open source development. Instead of relying on a single company's vision, Linux evolves through collaboration, experimentation, and community feedback. Ideas are tested, refined, sometimes rejected, and eventually improved until they reach a level of maturity that benefits everyone. This collaborative process may not always produce dramatic announcements or flashy marketing campaigns, but when the results finally arrive, they often reshape the industry in profound ways. The rise of cloud computing, the dominance of Android smartphones, and the infrastructure powering the internet all trace back to open-source technologies built on Linux. Now that same momentum is reaching the desktop in a way that feels different from anything we've seen before. The universal application packaging, improved security models, modern graphical systems, and stronger developer support are converging into a new generation of Linux computing. For longtime Linux users, this moment feels like the culmination of decades of gradual progress. For newcomers, it represents an operating system that is finally ready to compete head-to-head with the giants of the desktop world without requiring deep technical expertise. The real question isn't whether Linux will replace Windows or macOS tomorrow. The more interesting question is whether the traditional idea of operating system dominance even matters anymore. In a world of cloud services, cross-platform applications, and containerized environments, the underlying system becomes less about brand loyalty and more about flexibility, security, and performance. And in those areas, Linux is stronger than it has ever been. The combination of open innovation, modern packaging systems, improved security architecture, and growing developer adoption suggests that Linux is entering a new era. An era where installing software is simple, running applications is secure, gaming is viable, and customization remains limitless. For years, Linux enthusiasts have said that the year of the Linux desktop was just around the corner. Maybe that prediction arrived earlier than expected? Or maybe the transformation has been happening quietly all along, building momentum until it finally became impossible to ignore. Either way, one thing is clear. Linux isn't just evolving anymore. It's redefining what a modern operating system can be. And if the current pace of innovation continues, the next few years could reshape personal computing in ways that few people predicted.